So let's look at how you use our equations and the idea of our exponential changes, where your variable is the exponent, to look at things that change by percent. Anytime you hear about something that increases by 10% a year or something that decreases by 4.5% an hour, that's describing an exponential change, and we're going to figure out how to best work with it. So here is our situation. You can read through that. But even before we get into the specifics, I do want to kind of use this general idea to develop some shortcuts. Let's see how this happens. So on a given day in this mold colony, let's ignore the forever right now. I just want to imagine we are looking at a day in this mold growth process. However much mold you start with, I don't know how much it is right now, I'm going to call it X. We're going to take everything we have and we're going to add on 10% more. So this X represents 100% of the mold that we have. We want to add on another 10% of that amount. So from your previous discussions, I hope you remember that the word of in math means to multiply. So 10% of this amount means to take 10% times this amount. To do that, turn the 10% into a decimal, move the decimal over 2 spots, that's 0.1. So this represents that additional 10%, the full amount we started with, plus this additional 10%. Now, I hope you can see that because we have an X in both of these, we can factor that X out. It's a GCF, leaving us with 1 plus 0.1. What that means is, and this is going to save us a lot of time in the long run, is that to add 10% onto something is the same as multiplying that amount by 1.1. I don't know about you, I'd rather do this. That's just one simple calculation rather than doing, a multiplication and then an addition later. So let's turn this now into a general format. If X represents here the amount I was starting with, the 1 just means, hey, I'm going to keep everything I started with. Then we're going to add on some more, that extra percentage being represented as that decimal. We can turn that into our exponential change equation. So here it is down here. We will then go back and apply this to our particular circumstance. So what we're saying is the amount that you end with is always going to be equal to the amount you start with. And here is that discussion we just had. The 1 means, hey, keep everything you got, and then we're going to add on a little bit extra. So that R is your percent change is a decimal. Always move that decimal over 2 spots. Now, the reason this T is up here is because very often we don't want to do this just one time. We want to see what happens if we do this again and again and again. If you grow by 10% each day, well, then you would be multiplying by that 1.1 10 times. See how that works? So there's where the T comes in. This is a formula. Make sure you have it in your notes. Throw it on the back of your toolkit, that sort of thing. Okay, then, here we go. So in our particular case, I'm just going to take this and move it over here to the side. We're measuring the Petri dish at first, 4 millimeters squared, covered, 10% each day, covered at the start of the 9th day. All right, here we go. So then, let's take our general equation, and here it is. I'm just going to rewrite it in variable form. And then we're going to put in our specifics. We're trying to find out how much we end with. So that I don't know yet. A0, that's sometimes called, or A0, is the amount we start with. We started with 4 square millimeters. Each day we add on 10%, so turn that into a decimal. And we're doing that for 9 days. All right then. Let's just clean this up a little bit. So 4 times 1.1 to the 9th power. And then this is a thing you just throw right into your calculator. So hey, calculator, 4 times 1.1 to the 9th power. Let's round to the nearest 10th here and call this 9.4. So after 9 days, the start of the 9th day, you've got 9.4. square millimeters of mold based on that exponential growth. So again, the big keys. You use this equation when you are given a rate of change as a percent. How much you start with, how much you end with, percent as a decimal, and how long you are doing that compounding. It looks very similar, doesn't it, to that interest formula? Those of you that looked at that recording before, very, very similar. Okay, a second case. I'll leave it to you to read through that. You can do a quick pause. We're going to get our equation set up here as well. So our setup, we got a town and people are leaving for some reason. So each year the population decreases by about 1.7%. Notice here, we're going down this time. That's a decrease that's happening. We're going to need to take that into account. If in 2010 the population was 8,743, in what year would the population first drop below 6,500? Okay, let's take stock of what we know. In this particular case, do we know our ending population? We do. I want that to be 6,500. I want to see how long it takes to get there. Do we know our starting population? Yes, we do. 8,743. Do we know our percentage change? Yes, we do. Now, if it's a decrease, then instead of adding that 1.7%, we're going to subtract that 1.7%. Very important that you carefully read the problem you have. Otherwise, you're going to be misled. So 1 minus that 1.7%. Now remember, move that decimal over 2 spots. The decimal you use is 0.017. And then lastly, do we know how long it's going to take? No, that's what we're trying to find. Okay, awesome. Clean it up a little bit. Let's just do that subtraction that's in the parentheses. And 1 minus 0.017. I always like to just double check because I don't want to mess up that calculation. So 0.983. Now, here's the interpretation. If 1.7% of people are leaving, then the other 98.3% of people are staying. That's the interpretation of that number. Now, this is an exponential equation to solve. We've been solving exponential equations here now for a couple of weeks. Let's get this exponential by itself. So divide the 8743. So 6,500 divided by 8743. It's probably, it's not going to be nice. And the fraction doesn't even reduce. Now, here's the thing. Notice how that decimal is big and long? Please keep it as the fraction. If you round your decimal, your final answer is going to be off a little bit. We don't want that. Only round at the very, very end. So coming back here, I'm going to call it 6,500 divided by 8743. That's equal to 0.983 to the power of t. I want the t, so I need to find the exponent. Logarithms give us exponents. Please know this. Logarithms give us exponents. So we're ready to switch over to the log form. Log base 0.983 of 6,500 over 8743. That's going to give us the t that we're after. Or 93 rather. Okay, so it comes out to be about 17 point, let's call it 17.3. So t is approximately 17.3. Now be very careful. Is that the answer to the question? Was the question how long does it take? No. The question was in what year would it happen? So if we started in 2010, and if we wait another 17.3 years, well, that would be during some point during the year 2027. So when would the population drop below 6,500? At some point during the year 2027. So that's a good life tip for you when you've done all this work. make sure you actually answer the question that was asked. It wasn't how long does it take, it was during what year would it happen. So quick recap, then we'll look at one more. The only difference this time, well, I guess two differences. We were finding the t, but we also had a decrease. And when you got a decrease, make sure that you turn that into a minus there since you're going down. Solve it like an exponential equation. Make sure you answer the right question. For this final one, I'm just going to turn you loose on it. I want you to pause right now. Set things up. Try your best. When you get stuck, or if you get stuck, or when you're ready to check your answer, unpause things. Take a look through it. Okay, so general. So it says, what's the rate of change as a percent? Gotcha. So we're looking at that exponential change because it's talking about percent of change. And actually, I'm going to amend this just slightly. Per year. That's a little. I'm going to put another word in here, exponentially. So those two clarifications, just make it clearer that we're using this percent change model. So ending amount is starting amount, 1 plus r to the t. Here we go. Do we know the ending amount? Yes, we ended with 253. Do we know the starting amount? Yes, we started with 85. Do I know my percent change? I do not. Do I know how long it took? Yes, it took 10 years. Okay, let's solve for this r. So I want to get this by itself, divide the 85 over. I'm going to guess 253 divided by 85 doesn't come out nicely. Okay, so we'll just leave it as that fraction then. Again, do not round in the middle of the problem. Rounding should happen only in the final step. Next up, exponent of 10 needs to go away, so let's do a 10th root. And let's do a 10th root. All right, so over here on this left-hand side, I've got the 10th root of this fraction. And then over here, we've got just 1 plus r. And so then to finish, just subtract 1. Minus 1, minus 1. So the r that I want is the 10th root of 253 over 85 minus 1. And then we'll get a decimal approximation of that. So coming over here, for a 10th root, I'm going to temporarily move this. There we go. Let's see. It should be here in the functions, I imagine. Oh, goodness. Yeah, here it is. Okay, so, and it's in the wrong spot, of course. Scrolling down here, I want the 10th root of 253 over 85. Then go outside of the root, minus 1. So this is going to be then 0.115. So it's about 0.115. So remember, this is our percentage change as a decimal. So to answer the question, what's the percent change? Move that decimal back. So the rate of change is about 11.5% each year. So interpretation, in order to go from this amount to this amount, growing by the same percent each year over 10 years, you got to grow at a rate of about 11.5%.